welcome to Observatory Nights at the Harvard-Smithsonian Center for Astrophysics. I'm Christine Pulliam, and I'll be your host for the last time tonight. Now, 1 billion years ago, the only life on Earth was single-celled organisms. And the amoebas and bacteria that were floating around in that primordial soup had no idea of what was about to happen very far away in a distant galaxy. A long, long time ago, in a galaxy far, far away. Yes, indeed. For real. A gigantic collision was about to happen. 2 black holes merged. And in a fraction of a second, 4 suns worth of mass was converted straight into energy. And that energy actually created ripples in the fabric of space-time itself. Ripples known as gravitational waves. Those ripples spread outward in every direction, traveling at the speed of light. And 1 billion years later, those ripples began to approach a blue-white planet. Now, during that journey, the life on that planet had changed and evolved. Single-celled organisms had gone on to form multicellular organisms in a huge variety. One of those species even developed technology. They started building all kinds of machines, and 2 of those machines were designed to detect gravitational waves. And so, when those tiny ripples finally washed over our planet, we were ready, and we felt them. Now, the detection of gravitational waves is, I think, widely accepted as the science story and the discovery of 2016 when that was announced. But what you may not know is that detection took decades of work by literally thousands of people to design and build those machines, those detectors, the Laser Interferometer Gravitational-Wave Observatory. Tonight's speaker, Dr. Rainer Weiss, is a professor of physics emeritus at MIT and one of the founders of LIGO. Dr. Weiss is a fellow of the American Association for the Advancement of Science, the American Physical Society, and the American Academy of Arts and Sciences. He has numerous honors and awards, including an MIT Excellence in Teaching Award, the John Simon Guggenheim Memorial Foundation Fellowship, the Gruber Cosmology Prize, the Special Breakthrough Prize in Fundamental Physics, the Shaw Prize in Astronomy, and the Kavli Prize in Astrophysics. Please welcome Dr. Rainer Weiss. Thank you.
Thank you for having me. I hope this microphone...
If you can hear me in the back, raise your hand. Okay, good. I wasn't sure it was all going to work. Well, anyway, it's a pleasure to be here. I hope I can make myself understandable to you. If I don't, I will look at your faces. If you're looking at falling asleep, I'll slow down. If you look quizzical, I'll try to say a little better. So anyway, what we're going to be talking about is really pieces of physics and pieces of astronomy. And first I want to say here is the collaboration that actually was involved. About 100 institutions with 1,000 people. And you can find your favorite university up there someplace. And but these are the people who made LIGO work, and they are the people who are actually making the thing work now in this phase where we have finally gotten into doing science. And I want to start by motivating a little bit why gravitational waves even are something one contemplates, and how it happened that they were even being thought about. And the thing we know about gravity, all of us who have been to high school at some point, and maybe half a year in physics in college, learn that gravity is simply given by this gentleman, that's Newton, and by this formula, which I'll tell you what it is. There'll be 2 formulas in this whole thing. And one of them is this one. And this says that this was the basic idea, namely that two masses, and these are the 2 masses, attract each other. And they attract each other with a force that's given by this formula. And the force gets smaller as the square of the distance. In other words, when 2 objects are that far apart, they attract each other so much. If they get closer by half, what happens is the force grows 4 times bigger. So it's a quickly changing force. And that relationship explained almost everything we ever had to need to know about gravity. And it explained the moon program. It doesn't explain GPS. It doesn't explain your cell phone. In fact, if you didn't have the thing I'm going to talk about next, the cell phones wouldn't work well. Okay, but that's a wrinkle to the whole thing. And the big thing is that it works so well that people never wanted to change it. And when Albert Einstein was induced to come from Prague, where he had taken a professorship, to the very famous society, the Kaiser Wilhelm Society in Berlin, he was strongly advised by Planck, who was the physicist, the strongest physicist there, not to work on gravity. There was nothing wrong with gravity. Why mess around with that? Why don't you work on the quantum theory? Something really important and interesting. Einstein was very stubborn, and what came of it was another formulation of gravity, which I'm going to try to explain to you, but not, here's that second equation in this whole story. And that's Einstein's equation, which belies an enormous complexity. But what does this equation say? Einstein didn't like forces. So he replaced gravity, not by Newton's gravity, by an idea which we'll be talking about a lot. That the geometry, this side of this equation says, the geometry of space and time, and we'll get to what that means, is somehow related to the distribution of matter and energy. In other words, there are no forces anymore. We will see this in a minute. What exists now is an interaction where you put something into the space that's massive and has energy, and it distorts space and it distorts time. And then, as you'll see, what it does is things move, and here's sort of the image that you want to carry. Things move around in space because of that distortion. So let me explain this picture to you. And the best way for me to explain it to you, I'm sure many of you have kids, or if you didn't, you may have played in a jungle gym in your life, right? Who does? If you know a jungle gym, just raise your hand. Okay, great. I can use the analogy. A jungle gym is a great big thing. Kids play, you climb around. New York City, you had them all over the place. And what happens is you have all these rods that are put together in such a way that you get a rectangular cubes all over a space which you can fly around inside of and jump around in. Think of space, that you have mensurated space that way. You've built a gigantic jungle gym. It's very expensive. And it's all in your head. It's a Gedanken, okay? And what you do with that, you put a clock at every place where there was an intersection of the rods. Just put a clock everywhere. And synchronize those clocks. That's not trivial. You make sure they all read exactly the same time at the same moment of time. That's not so easy to do, and I won't explain it. But it's hard. And so now what you do is you plunk, and you're looking at this jungle gym from above a little bit. This is one cut in the jungle gym. And what something has done is they've put a great big mass in it. This is the sun. And it has distorted the jungle gym. These were straight lines as they are out here. Now they're curved lines. And also, you don't see the clocks. They were not put into this picture. But what happens now is that here's the sun, which has made a distortion in the jungle gym. Here's the earth, which has made a little distortion in the jungle gym because it's not as big as the sun. And now what happens is two things. When things move, like the earth around the sun, they get impelled to move along the shortest paths in that new space. And what happens is that the clocks, for example, a clock out here is keeping very regular time at each one of these points. But when it gets closer to the place where the curvature is large, they go more slowly. Clocks go more slowly in a big, strong gravitational field. And the same thing happens here. So the combination of time and space being distorted by the matter in it is the basic idea of Einstein's equations. Now, why did he bother with them? There were a lot of things wrong in his mind with the idea of Newton. First of all, how does information get around in Newton? In Newton's thing, if somehow something happened and a mass was pulled away and disappeared, that information was instantaneously transmitted over the entire universe. That was not something Einstein could tolerate, not from after 1905. Everything had to have a finite speed. The fastest things could go is the velocity of light. Information couldn't go any faster than that. So that was a fundamental flaw, one of the things he was worried about. The other thing that he was worried about is it didn't work for very fast-moving masses. And now we know that, in fact, as we'll learn as I get this talk, the theory that he developed worked exceedingly well. So now, here are the things that he immediately happened to come upon. These are itty-bitty little tiny effects that are different in Einstein's theory than they were in Newton's theory. And they were puzzles. They weren't troubling everybody. And for example, here's one of the puzzles. This is a thing which, it was the idea that the planet Mercury, which you have a very hard time seeing, it's so close to the sun. There's the sun. In Newton's theory, the planet Mercury would have gone around an ellipse like that and stayed going around over and over and over again. But it doesn't do that. Astronomers found, by the end of the 1800s, they knew pretty well already that that it would do a little sort of Lissajous thing. It would go around like a spirochete, like that, goes around. And this thing, what's called in this case the perihelion or the aphelion advance of Mercury, was a very troubling idea to people. They didn't know where it was. And there's a lovely book you can read about how people tried to solve this in the 1890s. They thought there might have been another planet between Mercury and the sun. And they even gave it a name. They called it Vulcan. And there's a book called Vulcan. And you can read it. It's a wonderful story. And, and they couldn't find the damn thing. And it's very hard to squint because, they were confused over and over again. So, okay. Anyway, Einstein, when he formulated his theory in 1915, he had this enormous triumph that he could explain that non-closed orbit. And it got it exactly right. In fact, the story says that he couldn't sleep for a week after he found that his theory worked and showed that. So that was a big triumph for this new theory, which people thought was totally unnecessary. Here's the other thing, and this is got a little politics. This story was, there was a prediction made by his theory that you would get, here's the sun, and here's again this jungle gym. You're seeing a cut in it. And if you looked at a star, let's say a star that was really over here, but it turns out that if the light travels from here, it bends around the sun. It gets bent by the curvature of the space-time that's generated by the sun, bends this around. So the star that is there, you actually see with a telescope there. Okay? That's where you see it, because you think it isn't bent. Okay? And that was a huge thing, and this guy Arthur Eddington, made a huge fuss about it in 1919. And the interesting story behind that is that Eddington was a Quaker. And they had just lived through the World War I. And Einstein became an enormously famous person exactly as soon as Eddington and a group of people, Dyson and other astronomers, went to eclipses and saw that the light from these stars bent around the sun a little bit. You have to use an eclipse to block the sun to be able to see this. And then they had, the data wasn't all that wonderful. I'm not so sure they really saw it, but they believed they saw it. Okay? And to Eddington was absolutely critical that they saw it because he was going to make a case out of this. His case was, he was a Brit, and he was this German Jew who had invented this theory, and they were on the opposite sides of a war. And nevertheless, they could still do science together. And to Eddington, that was a symbol that man was above the petty battles that had killed 2 million people, okay? But that there was something solid that was there that you could use. And so that's why he forced the whole issue. Einstein would not have become the famous man he was without Eddington having that in his head. He wanted to make that point very strongly. Now, in our own time, a very other big important part of this was discovered by a graduate student, Russell Hulse, and Joe Taylor, who was a professor at the time when this was going on, a professor at the University of Massachusetts. He was, I think, a Harvard student. He had been a Harvard student. And what they were doing is this experiment. And this was one of fortuitous, and why I'm telling you about this is the first really instinct that people had that they were seeing something due to gravitational waves. And I'll tell you in a minute what they are. But here is the first evidence that was real. And what it is they had a telescope, a radio telescope, the Arecibo telescope, and they picked up a star. They couldn't see anything, this was all radio. And they picked up this star, which happens to be a star that's about the mass of the sun, but it is much tinier. It's about the size of the city of Cambridge. Tiny. And it has a huge density. And it's a neutron star made mostly of neutrons, the thing inside of an atom. And so this is a tiny thing, and people had discovered that these are pulsars. These are things that are spinning pretty quickly, and they have a little searchlight on them, and every time they go past the radio telescope, they go blip, 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 and you pick that up. And this star, they saw it because it was doing it about 17 times a second. But they noticed something very strange about it. They noticed that for about 4 hours of the day, it was getting a little faster than 17, and 4 hours later, 8 hours later, it was going away. As we will see in a minute, it was going slower. So it was going fast on, let's say, here, and it was going slow when it's over here. So what's going on is the fact that they had found out by this that this wonderful little clock, which is this star, was actually in orbit around something else. It was turned out to be a thing they couldn't see, and it was another pulsar. So this is this system. It has a 17 hertz period, 17 hertz frequency, goes 17 times a second, sort of the lowest note on the piano. And these two guys go around each other once every 8 hours. And that was a fantastic laboratory for doing tests of general relativity. And the test they did was this one. They noticed, this is the discovery, I think, of gravitational waves. What they found is that as they followed these two guys went around each other. You're going to see this orbit motion over and over again in my little talk. This orbital thing was going on, and what this orbit was doing is it was speeding up. It was getting faster. And when in gravity something speeds up as it's orbiting, it's getting faster, it's losing energy. It's a little persnickety, but that's what happens. And let's not worry about that. You can ask me that later, why that happens. But the things move faster when they get closer together, but don't have as much energy, even though they're moving faster. That's because there's energy stored in the gravitational field. But let's talk about that later. So, but the important measurement they made over many, many years, this is epoch down here. This is 1973 to 2000. I'm sure this goes on further now. And this is what's here is they were taking the time it takes for these to go around each other by just looking at those pulses. And each time that it went every 8 hours, that little 8 hours got a little shorter. So this is the sort of in seconds. And they noticed the dots. Here are the dots. This is the thing as it was getting shorter and shorter. This is the data they had over all those years. And this line that goes through them is not a fit. It's the actual prediction of the Einstein theory if those two stars are losing their energy to gravitational waves. Okay? So that was an inferential first measurement. It won both Hulse and Taylor the Nobel Prize in 1993. So that was, I think, and it was enormously debated before that, whether gravitational waves were real or not. This was, I think, the critical observation. Okay. Now here's a gravitational wave. I want you to imagine it, and I'll walk you through this. You don't get too dizzy looking at it, okay? But what it is, what you've done is you've done a little piece of the jungle gym. You've sprayed out all these little particles. Those black dots are those intersections of the plane in the jungle gym. And the place that's right in the middle, where there's a red square like that, is you. You're right there. And what this is a gravitational wave coming out at you from the screen. And this is what it does to the little masses you might have put at the intersections of the jungle gym bars. And you'll notice something interesting. For a while, they're getting closer together in one dimension, and they get further apart in the other one. So there's a contraction in one dimension, while simultaneously there's an expansion in the other. And it keeps flipping back and forth. I hope you can see that. That's probably what's making you dizzy, okay? But there's a much more important thing that's also true. So the gravitational wave is moving at you. It's doing its dirty work perpendicular to the direction in which it's moving. Okay? It's coming out at you. Now, there's one very important characteristic of this, which is fundamental to how to detect a gravitational wave. And that is that you'll notice that, for example, let's look at the two spots on the east and west side of you. You notice these two are moving. They're not very far apart, and they're moving some. But you look on this line, way out there, and there, they're moving a lot, right? And the ratio is a constant in that system, which is the ratio of the change in separation, delta L, the change, divided by their separation. So delta L divided by L is a constant. It's a constant in the sense that at any one moment, this whole line, let's say, is expanding, and the delta of these two guys divided by their separation is the same as the delta of little guys divided by their separation. And it's also going in the other direction. It's compression in one direction. It's expansion. And that's the image I want you to have of a gravitational wave, because that is the image that, in fact, Einstein had of it. So now comes the first people who will try to do something about it on the ground. In other words, once you have an image like that, you can say, aha, I can make a detection for that kind of motion. And that's what Joe Weber did, who was a scientist at the University of Maryland. He's unfortunately dead now, but he had the idea, along with John Wheeler, who was at Princeton, that maybe you should finally do some measurements and try to measure gravitational waves. And we'll get to what really it takes. But Joe Weber, here he is with his apparatus. His apparatus is a gigantic bar. It's a huge bar of aluminum. It's like and you know, you can see him putting little sensors on it that measure the stretching of the bar in one dimension and the compression of the bar in the other as a gravitational wave goes through it. That was the basic idea. And, well, okay, to his misfortune, he saw something. In other words, in fact, it was quite a scandal. In 1969, he published a paper saying that he had discovered gravitational waves with a device like this, but he had made 3 of them. One in his lab in Maryland, another one in a golf course about 8 miles away from his lab, and he put one in Chicago, far away, in the Argonne Laboratory. It's about 1,000 miles away. And what he was seeing pulses that were coincident, pulses of something driving those bars that were coincident, typically 2 or 3 times a day. And that made him convinced that he was seeing gravitational waves. Well, it turns out the whole world got on that, because when you make a big announcement like that, you know, everybody says, wow, that's spectacular. But the lovely thing about science is that you can check up on it. And I think there were 8 groups in the United States, probably 4 groups in Europe, 2 groups in Asia that all built the same kinds of things he did, and they saw nothing over a matter of years. And that caused a lot of trouble a bit. But the field, some people decided they would try to continue, because the idea of looking for gravitational waves from astrophysical sources had some merit. Most of the people dropped out, but there were some people who stuck with it. And now here is the story that I want to get to. The people, there were a couple of groups who were thinking of doing this by other techniques, and that's what I'm going to show you. But let me get to how small the strain is. That's what that delta L over L, that change of distance between them compared to their distance, is tiny. If you want to do gravitational wave physics, and this is not an equation, this is just something we're going to talk a lot about. Namely, H is the thing that's called the strain. That is the gravitational wave strength. And if you start making numbers using Einstein's theory for anything you can think of in astrophysics that might generate gravitational waves, you've got to be able to measure at least a strain of 10 to the minus 21. So I'm going to use this 10 to the x notation. Why? Because it's a hell of a lot simpler than saying billion, trillion, billion, billion, trillion. I can't even keep it straight. So I'm going to teach you how to use this if you don't know how to do it. See, what this is a fraction. It's a fraction, a decimal point with 20 zeros, 0, 0, 0, 0, 0, 20 of them, and then a 1. 20 of them, 1. Okay? That's a neat, compact way of writing such a small number. So 10 to the power 10 to the minus 21. Now, if you multiply that by the length of what one of our detectors is, which is about 4 kilometers, you wind up with what you have to be able to measure to make a gravitational wave measurement is about something you have to be able to measure 10 to the minus 18 meters. And now I want to give you a feeling for 10 to the minus 18 meters. Okay? So this is physics, not astronomy, but if you want to get into this business, this has got to become visceral. Okay? And you'll understand why. Okay, so you start with a meter. I wish all of us knew what a meter is. It's 3 feet. But in this country, they don't use a meter. And so, okay, we go from 1 meter down to 10 to the minus 18 meters. Let's do some steps. The first step is the human hair. Well, we divide a meter by 10,000. Okay? Well, a human hair is about 10 to the minus, it's 10 to the minus 4 of a meter. 10 thousandths of a meter. Yeah, you have good experience with that. All of us have here, or most of us do. Then you say, okay, well, you got to go another 100, and then you get to a wavelength of light. Now, all of you can experience that directly too. Maybe not in this room, but when you go home tonight, if you haven't got a good feel for it, take a look at a mercury arc or any of those blue lights or the yellow lights, and look through a slit you make with your fingers. Let's look through that slit in the fingers, and you'll notice little black bands when you do that as you squeeze them together, and you'll find out. If you use a little algebra and a little geometry, you have measured the wavelength of light. And the wavelength of light is still something very small. It's about 10 to the minus 6 meters, and you can still play, and you still have something still that you can understand. And you can still go one more step. You can divide by another 10,000 and get to the size of an atom. Now, I'm going to give you a little experiment you can do for yourself and see what the size of an atom is. All of you have medicine droppers, I'm sure, or I can find one. You take a medicine dropper and put a little bit of olive oil or some oily stuff in it, and put it in there, and go to the bathtub, put some water in it, and put some dust or something, or take your vacuum cleaner and put dust in it, and drop a drop out of the medicine dropper, a thing you measure the diameter of. You don't have to do very well. Just look at it with a little ruler behind it, and if you'll be a sort of a couple of millimeters, and then you drop it, and you'll see this thing spread out over the water. Okay, and then you've done an experiment that tells you how big an atom is. You look at the volume of the drop that you made. Most people know how to do that. 4/3 pi r cubed. That's the volume. And then you look at, with a ruler, you measure the area of the big patch that you made in the bathtub. And that gives you the area. Now you have that. You don't have to do any more. If you know the volume of the drop and you know the area, the volume has to be the same. So you know the height of that swath that you made in the bathtub. And when you do that, you will get about this number. Right? You'll get down to about 10 to the minus 10 meters. So that's still within your realm. But we're not there yet. Okay? So it turns out that, okay, then you start having to believe me. Okay? And so you divide by another 100,000, you get to about the size of a nucleus. That's the nucleus inside of an atom. And you're still not there, so you divide that by 1,000. And so we're talking about 1,000th the size of a nucleus. So that's the dendrite that you have to go to appreciate why people took 40 years to do this. Okay? All right. And so there were two things that you had to do. You had to, and I'll show you the both, but only very schematically. You're going to use light. That's what the idea is, to make a measurement of something. And you're going to have to change, you have to make it so good that you can measure something like 10 to the 12, a million times a million, 10 to the 12 better than the wavelength of light, to be able to see the motion that you have to see. And we'll talk about seeing that in a minute. And the other thing, you have to make sure things don't get kicked around by so much. And we'll talk about that more in a second. So what you see here is the method that supplanted the Weber technique for doing this, and is also the basis for the way LIGO works. So this is an animation, and here's a laser. It doesn't look like a laser, but believe it, it's a laser in a minute. And this is a beam splitter. This is a device that'll take light, and half of it gets reflected to this mirror, and half of it gets transmitted through that mirror and goes to, through this beam splitter and goes to that mirror. And then these reflect things back. And then light goes back to the laser and also to a photodetector. And the photodetector is right there. So let me get this all started. And so you'll see what this is called an interferometer. And what is happening is that light, wherever there's red, there's light power. And this wiggly thing is the electric field in the light. There is an electric field in the light, and you need that to keep track of what's going to happen here. Both sides are reflected, and now you'll notice they're both out of phase with each other, and no light, there's no red getting to the photodetector. The reason is light has spent equal times in the two arms. Now you go and do that thing which you saw in the dots that I showed you. Stretch one and make one show, and you notice light goes here. When they're equal again, there's no light, but when they move in and out to each other, there is light, and that is the basis of the detection. In other words, a gravitational wave that comes down on that thing you have just witnessed will stretch one of those arms, move one of the mirrors out, move another mirror in, and keep doing that. And it'll make light change at the photodetector. And it's no more complicated. The whole idea is no more complicated than that. Now, who's lost? Nobody's admitting it. Okay. All right. Anyway, that's the basic idea. And now you have to use this in a way, this is the way it's actually done, and this is where that factor of 10 to the 12 comes in, all the cunning and the trickery to make light be able to make a measurement of these mirrors. And this is actually the instrument. And let me show you the thing you're already familiar with. There's the laser, there's the beam splitter, and there are those far mirrors. There's one, and way over here. And now there's some new mirrors in this thing. That's the photodetector. We had that before. And the new things in here are these mirrors, this one, and that one. Well, they're pretty straightforward. What they do is they take the light, partially transmit it, and bounce it back and forth many, many times, something like 300-400 times. And they do the same thing over here. And what you do is you endeavor to make it so the light spends the same time going back and forth in here as it does in here. So the time is still the same. And everything happens, and the light still, you can make it so that no light goes to the photodetector. But what you've done by this is you've made it so that the system is 300 or 400 times more sensitive. One way of thinking, it has longer arms. That's one way to think about it. But there's this other mirror, which is actually quite important also. And this mirror does something quite spectacular. What it does is, as I told you, no light, and you saw in that animation, no light gets to this photodetector. That means all the light that is injected by the laser comes back to comes back to the laser. That's what it does. Light doesn't get lost. If it doesn't go to the photodetector, it comes back through that beam splitter, goes back to the laser. Well, the laser hates that. And so what happens is you put a mirror in here which is partially reflecting, which is very cleverly made to do the following. There's a light coming back from the interferometer, and it's going to go through here and go back and hit the laser. But there's also light coming from the laser going into the interferometer, but it's also some of it's being reflected by that mirror. So there are two beams of light, one that went out of the laser and is coming back, one that's coming out of the interferometer and is coming back, and you make those two just cancel each other. You make another interferometer. And that says you've taken all the light that comes out of the laser and put it inside the interferometer. And what that does, for example, is you might have 25 watts of light coming out of the laser. You might have in here, because the light is bouncing, rattling around in here, you might have 500 watts of light in here, and you might have half a megawatt of light in here and there. And that's where you get that big factor of getting more light and being able to use it in a clever way to make these small motions of those mirrors. Okay, that's one half of the big fight that we had to do, and that took some number of, probably 20 years to develop. The thing that was just as hard is the part that those mirrors that are doing the reflecting can't move more than 10 to the minus 18 meters due to something that's kicking it around. And there's plenty of stuff kicking those mirrors around. And I'll give you one that you're not getting seasick right now, but right now you're in a place right here where the ground is moving by at least 2 microns, 2 times 10 to the minus 6 meters. Everything is shaking. I mean, you don't sense it because it's so small. You know, it's much less than a hair, but that would completely screw up these measurements. So you have another factor from 10 to the minus 6 to 10 to the minus 18, so another factor of 10 to the 12. In doing something different, you want to make sure that nothing is moving those mirrors except the gravitational wave. Okay? And that's much harder to do than getting the light to do that tricky stuff that I was just describing to you. And so here are some tricks that are used. One trick is to make a pendulum. Now, I won't describe it anymore as to say the following. If you tie the top of a pendulum, a pendulum is a thing that goes wobble, wobble. Here's the top of the pendulum. And if you move, here's the top of the pendulum, which is tied to the ground, and you move that slowly, the pendulum and the bob move together. I mean, the ground is moving the top slowly, and then the pendulum will move with it'll move. I showed this as a demonstration when we did this, but I can just do it by hand. And now, what happens is you move quickly, this ground, the high frequency, it turns out this stands still. And you can prove to yourself, I won't take my belt off and show it to you by putting a thing on and my pants will fall down, but the thing is that you can do this for yourself also. It's a very easy thing to prove. And so you can do this, and you have to do it very elegantly. It's done 4 times. Here's the ground is attached to you don't see the ground attached, but that's where it's attached. In fact, this thing is attached to this device, which we'll get to right there. And there are 4 of these. There's one pendulum, that's this mass and all of those, then this, another mass, and then this mass, and that mass. So there are 4 pendula in series. And all of those, you multiply their isolation. That's the way it works. So that's part of it. You get a big factor out of that, but then you do something very slick. And this is what, I'm not going to describe it to you in detail. I was trying to find a better picture of this, but I will tell you in words what it does. How many of you have ever been on an airplane and have these fancy earphones that allow you not to hear the engines? I mean, these are these earphones which you can buy nowadays, which you can hear the music, but you don't hear the outside so well. Have you ever figured out how they work? Okay, I'll tell you how they work. They have a little microphone inside there, and the microphone picks up the noise from the airplane. There's a loudspeaker, a little driver that makes noise, but there's also a microphone picking up the sound from the outside, and it amplifies that and flips its sign around so that it cancels the airplane noise that gets to your ear. and the music is not canceled. That's the way it works. So it's the same idea here. What you do is here's the ground, and you do this over again, and you do it 3 times over, this trick. You make a device that measures the ground motion in X and Y, let's say in this dimension and that dimension, and then you push on it. You push on this thing to make these things read 0. In other words, they would measure the ground. If you turn off these pushers, they would just follow the ground. But then you amplify the signal from these devices, feed them, invert them, and so you know the devices which we call seismometers. You do that once, then you do it again, and you do it again, and then you hang this fancy thing here from that, and there it is, that's this suspension, and you hang it. And this gets you that factor of 10 to the 18. That's called an active vibration isolation system. And of those of you who build telescopes are worried about ground noise, you might want to pay attention to this. This is not a bad idea. You can do it more cheaply than we did. And you can do it if you want to get rid of ground noise. Using a sensor for the ground noise and nulling it in a feedback system is a very effective way to make a vibration isolation system. Okay? All right. So, now let me tell you a little about the discovery and where we're going. There are 2 detectors in the United States, one in Hanford, Washington, and another one in Livingston, Louisiana. There's another detector, which we'll talk about a little later. That's in Italy. That wasn't running at the time when we made the detection. There's another detector you'll see in another picture, which is a research detector in Germany. And we'll see at the end why there are many detectors and why many more are trying to be built. We'll get to that as we talk about the science. Anyway, I'll take you a little quick tour through LIGO. This won't take very long. And what it is this is the LIGO facility in Louisiana. You can see trees. And this is what it looks like from above. This is the one in Washington. It's in a desert. And this is the beam tube, in which size there's a vacuum system. And you can see this big mountain in the background. Here is the same thing in Louisiana. And if you work on LIGO, you can sometimes, if you live in the buildings, you can't tell whether you're in Louisiana or you're in Hanford. You just don't know. And here are people working on a laser table, for example, at the output table. And here's a control room in Louisiana, and people are learning being taught how to operate the interferometer. So it's a big installation, 2 big installations. Cost about $1 billion when you put in the 40 years of support into all the groups that worked, and the installations themselves, the building of the installations, and the operations of the installations cost about $40 million a year. So $1 billion has gone into this experiment of your money. And so this is what we saw when we made this discovery. And what it is this is the output of one of the interferometers. This happens to be the output in the Livingston. This is the one in Louisiana or Livingston. I'll probably not be sharp about how I say it. This axis is the time, so you can see it's fairly short. It's 0.3 seconds. This whole thing is about 0.15 seconds. And this is the strain. And you'll see that it's about 10 to the minus 21. So the biggest was. So that number that people had calculated for what you needed to have wasn't far off. And what you see here is something that's noise. Up here it's noise, and it's noise over here. But there's something coherent building up in this. And now you take a look at this thing, and you see this in Hanford. This is now the one in Washington State. And they look similar. We'll put them on top of each other in a minute. Again, noise over here, noise over there, but something that if you now look at them and translate them, because it takes time for the signal, the gravitational wave, if you think that's what it is, to go from Livingston to Hanford, it takes about 7 thousandths of a second, 7 milliseconds. And here is, okay, I'll superpose them in a minute. Let me do it to superpose them here. You can see them on top of each other. And what's been done is you've shifted the blue guy 7 milliseconds in a direction such that they superpose with each other. That makes for the travel time of the gravitational wave from Louisiana through the Earth. The Earth the gravitational wave doesn't give a damn about what it goes through. It goes through everything. And it shows up in Washington State. And you can put the 2 signals on top of each other. They're not perfectly on top of each other because of the noise in the signals. Okay? But they're sufficiently on top of each other that now if you go back, and this is the thing that should have been in the other drawing, there is buried in here a smooth curve, which is not noisy. It's a little easier to see over here. And that is a theoretical curve that you can calculate from Einstein's equations once you think you know what you're looking at, and you find the best fit to. And that is indeed, it turns out to be 2 black holes that collided to make this. there's another representation of this, which is to write it in terms of, and this is the thing that made the big noise, it made everybody so happy in Washington. This is the same time scale here, but now instead of giving you the strain, this is the frequency of the strain. This is the sound it makes. In other words, the bottom of the piano is about there. The top of the piano is off scale, but this is sort of middle C, right about there. 256 is middle C. And here is the spectrum of it in Livingston. There's the spectrum as seen in Hanford. And let me play it for you. Can you hear that thud? Okay. It's like you making a glissando very fast on the piano, okay? And so we tricked it up a little bit so you could hear it better by changing it. Okay? That's the chirp that caused all the trouble. Okay? And now I want to show you, at least this is now a movie that was made by people at Cornell and at Caltech about what this was. And it fits very beautifully. You can see the same kind of shape. This is the signal, the gravitational wave signal on the bottom here. And this is a cut in the jungle gym, which you'll see of what these two black holes are doing. So let me get the things going. And I'll describe to you what's happening. You're going to look down on the jungle gym like we did, but it's a smoother looking jungle gym. There, the two black holes are those two guys. They're pretty far apart. And here's the jungle gym, but now it's continuous. And wherever there's red, the time has changed. It's getting very slow. When it's green, the time is fast. And these little arrows that you see are the stretching that takes place in space. If you happen to go there, you would be stretched along those lines. By a lot, by the way. And those holes, you see the two black holes are there. You can here's the time, and this will change time on you so they can concentrate and you can see what's happening to space-time as they get very close. I mean, the time is getting outrageously slow in here. Eventually, it just comes to a stop inside. I mean, I'm talking about the real time that's kept by clocks. I mean, not only that time. And so here, you're getting very close to a storm, and these two guys are about to meet and make a new black hole, a bigger black hole. And that's what we were seeing, okay? And I should have pointed down here because the waveform is still doing it at the bottom here. And this was not possible to make. That movie is a modern thing also. 5 years ago, we couldn't have made that movie because people didn't know how to use computers and solve Einstein's equations. They're enormously complicated to solve. And so it turns out that this was a big event that now we can do it. And so we discovered other black holes. This is the first run we made. And this is the one we've been talking about. It's very short. This is, again, time versus strain. And then we saw another one, which we're not sure of. That was around, you can see that was around 10, 12. That looks like October. This was in September 9, 14. September 14th, 2015 is October 12th, so Columbus Day. And that one we're not sure of, but it sure looks like a black hole. And this was done by other techniques. This is what you could see by eye. These you had to do very fancy mathematical techniques to pull out of the noise. And this is one we're sure of. And these are, this is later. This was in around the day after Christmas in that year. And here are the sort of parameters that go with that. These two guys, in short, is because they're big masses. 36 solar masses and another 29 solar, and as it's a little different than what you said. It's 3 solar masses went into energy. But that's still plenty, and it outshone the universe. Those people, those critters on the Earth didn't see it, but the people that were closer to it, and this is 1 billion years away from here, 1 billion light years away where this happened. But they were shook up dramatically. But the energy was so bright. There was so much energy put out by this in just plain old watts and joules that it was brighter than the entire universe in light. The entire universe in light for that fraction of a second. Then we found these others. These are more modest. These are still stellar black holes, and they lose. This is 23 solar masses, 13 solar masses, 1.5. This one we're not sure of. This we're very sure of. And so this is the catalog we have right now. We're running again. We are seeing things. I can't tell you much about them because they haven't been analyzed, but we see signals. Some of them may be baloney. Some of them probably are right. And but things are not there. This is sort of interesting that I encountered in New York when I went to New York right after the discovery. I see this advertisement in the New York City subway, and I can read it better here. Scientists found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in closet. Now, remember, this is the subway in New York, and this is sort of a week or 2 weeks after our discovery was announced. I mean, to me, it's sort of amazing that it hit the public like that. I don't know if these guys are very interested in that, but this is a New Yorker cartoon. It says, this guy's saying, was that you I just heard? Or was it two black holes colliding? See? It's a chirp from that time. Okay, so that's what greeted us with this discovery. And that sort of was amazing. Someday we can discuss why this hit the public in this wonderful way. But it did. Now let me tell you some problems, and we're getting near the end. This is the best we can, now this is for astronomers. This is the best we can tell with the different, these are the different sources that we saw, the three. And this one that we made all the fuss about is this guy. And this is a picture of the sky. And this is the celestial equator. And this is the North Pole, the South Pole, and in declination. And so here is the best we can do, a huge thing that's about almost 300 square degrees uncertain in where we think that source is. And how do we even know that? We know that from the delay between Livingston and Hanford. That's all we know. You can't point these detectors. They're not like telescopes. And then the other one which we believe in is the yellow one, and that one is even worse. So we can't tell anybody who is a respected, I mean, suppose you tell an astronomer, go look in 1,000 square degrees for this thing. Okay? They will laugh at you, and they do. But some of them are hardy enough to try it. And it turns out some of them are trying to find an analog to this. That would be a wonderful thing to do. It would tie these discoveries to the more ancient and much more venerable science of astronomy. That would be very valuable in trying to understand. In fact, right now we don't know where these black holes come from. And you could ask me about it. I don't think we have a good idea about it. So here then is the thing that is in the future. And that is that here are the two detectors I talked about. Here are the ones I did mention, but I didn't tell you where they were. These are in existence, all of these. And Virgo was hopefully going to run with us, but they're going to do it now. They're finally getting ready to do it. They weren't ready when we were running, and they were not part of the discovery for that reason. But they're very important to the business of trying to find out where that source is on the sky. You need to have that. Otherwise, because you get another time out of that. See, you get a time difference between here and there. In our case, the source was over here, came through the Earth, went zap like that. Well, these guys could have, there would be another time difference between these two and those two. Okay, we need that badly. And it turns out to do it really right, you need it, as you'll see in a minute. These are two proposed detectors. This one's being built right now in Japan in the Kamioka mine. And that will be ready, we hope, in 2018. And there is a proposed and actually now agreed upon detector in India, one of the LIGO detectors. We had a spare set of parts for making another interferometer, and that's been given to the Indians. Okay? And that hopefully will be operating in about 2024. And this is what it'll do. This is that same kind of celestial plot. And you can see the uncertainties if we have Hanford. Don't worry about that H. That's Hanford, Livingston, and Virgo. If we all three were running together, we could have done a lot better. I mean, this is sort of still probably 30 degrees square, something like that. But there are places where you can do, the error circles are not so terrible in some places. But suppose we got LIGO India. It'll look like that. And many of the places are now about the size of what you were describing, namely the size of the moon. And that is still horribly bad for an astronomer, but it's not hopeless. I think that's right. I mean, you can get astronomy, well, some astronomers will take a look over a square degree, square half degree, something like that. Okay, so that'd be very important. Okay, so that's the future. And our future is very much the same as it was in electromagnetic astronomy. Remember, we had optical astronomy first, and with Galileo beginning it, and that's how we learned a lot, then radio astronomy, and then infrared and on one end, and X-ray astronomy. This has been sort of the mainstay of our whole understanding of the universe. These different channels, they all tell us different things. And in fact, that's coined a word that's called multi-messenger astronomy. And that's what we have started to open. Already people have, I mean, it's been done electromagnetically. That distinguishes these things is they're all electromagnetic radiation that is sending the signals from those heavenly bodies to us. And so we're picking it up as electromagnetic waves. And now, when we open now the gravitational wave window, which we're beginning to open. So here's Hanford. And here you have again, but it's again separated in different wavelengths. It's sort of interesting. And this is LIGO. And it looks for sources that have periods of milliseconds. 1,000 milliseconds. I mean, no, 100 milliseconds to maybe, that's wrong. I said the wrong word. It's something like tenth Yeah, 100 milliseconds is right. 100 milliseconds to about a millisecond. That's sort of the band of that, or frequencies from kilohertz to about 10 hertz. And that's all we can do for complicated reasons. I'll gladly explain them to you. It turns out there's a whole mission that was just about as old as LIGO, and that's called LISA, and that's putting a interferometer system in space where there are 3 satellites, and you measure the distance between these 3 satellites continuously with lasers. There they are in an equilateral triangle, placed at the Lagrange point behind the Earth in the same orbit as the Earth around the Sun, and they will hope to do minutes to hours for gravitational waves, and they will see black holes like the ones you were describing. 10 to the 5, 10 to the 6 solar mass black holes. And they will look at small objects going into a big black hole like that. They will also look at white dwarf stars in our own galaxy radiating gravitational waves. So that's a very interesting, mission, and it will also add to those things on the ground. For example, they'll see those black holes way before we do, and they'll tell us exactly where to look, for example, if you want to get an electromagnetic counterpart. Then there's another complete other project, which is elegant. This uses the clocks that are in the sky, those pulsars, that you know already from the first discovery of gravitational waves. They are distributed out through our galaxy, and with radio telescopes, you look at a whole bunch of them. Some up there, some down here, some over there, and you watch how their rate changes. And if you see a thing where the rate of pulsing is going here, and down here it's growing, but slowing down over there and slowing down over there, you have a chance that you're looking at a gravitational wave that's come through the galaxy. But now what they're interested in doing is they're looking then at things that have periods of years to decades. Okay? That's about where they can look. And then there's an experiment that's even actually being done here at Harvard and many other places, Princeton, and this is my favorite topic, is that actually this is much more complicated to explain, but I'll just say it, and then you can ask me if you're really interested. It's a way of looking using the electromagnetic radiation from the Big Bang, from the cosmic background radiation, which was the radiation that suffuses all of space, that we know now is at about 2.7 degrees Kelvin. It comes from everywhere. And using that radiation and the polarization of that radiation, how the electric field vector points, and using that as a way of detecting primeval gravitational waves, because what they do is they make density changes in the plasma, and what they do is they make patterns, density changes which are dense here, dense there, not so dense there, these quadrupole patterns, and these patterns will make a very special pattern in the sky of the polarization of that cosmic background radiation. I gave you a lot of jargon there. I tried to avoid jargon, but it's harder. I cannot explain it in a very much simple way, except we could spend the next 20 minutes talking about each individual jargon word, okay? And the thing is that that was tried. People have been looking for this. There was a discovery made about 2 years ago where people thought they were seeing this radiation, which is spectacular if they see it, because it would tell us about what happened at the instant when the universe got formed. Because gravitational waves go right through everything. See, we can't, with our light or electromagnetic waves, look at the beginning of the universe. You can go about 300,000 years, and then after the explosion, that's as far as back as you can go. With gravitational waves, you can go right to the microsecond when it happened. And then you can really see what's going on at the instant when the universe formed out of a vacuum fluctuation. So, I mean, that's spectacular science. And the thing is that, and people thought they were seeing this from an experiment at the South Pole called BICEP. And a large group here at Harvard is doing this. So people at Princeton, and well, not Princeton, but these are people at Caltech and at Stanford. And unfortunately, they were careful, but they were a little ambitious and they were a little too quick. And they were maybe seeing something of those patterns, but what they're really seeing, we now know, was also some of it coming from dust itself. The dust in our own galaxy makes patterns also, and these patterns are not different than you get from the cosmic background of gravitational waves, so in the polarization pattern. So that experiment is not over. People have added channels to it, so they can pick out the dust and separate it from the other effects. And there are at least 3 or 4 other groups in the world doing this experiment, including China, in the Tibet. So if that is going to, I think in your lifetime, maybe even in mine, this thing will have a result. It may be 0, but it may have a most spectacular result. So now let me just quickly show you who did this all. Here's this group at Caltech that I can't give credit to everybody. This is the only way I can do it. And I can show you a picture of them, and you'll see this is the MIT group. You can see Nergis. I'll point out some of the people. And Peter, there's Peter Fritschel, who happens to be represented here. And here's Nergis. And then, well, there's some other, there's David Shoemaker. Many of you know these people. And then there's the group at the Livingston Observatory. That's about the same size everywhere. Caltech is biggest because they do the fiducial, they do the money, the financial part of the project. And then there's another group at Hanford. So that's the group that did it. Thank you. Yeah.
So, there's got to be some good questions out there. Yeah, go ahead. Oh, yeah.
No, you go ahead. I mean, you point to who you want. You know these people. I don't.
The gentleman in the green plaid is going to ask first.
In the LIGO, are those optical elements kept cold?
No, that's a good question. And I didn't. And there's a lot of things I had to leave out to make it so I could get done in an hour. The other point that he's pointing to is that another noise besides ground noise, and is the fact that if we operate at room temperature, which we do, okay, right now, everything shakes a little bit because it's called Brownian motion. And because at room temperature, there's sound waves running everywhere, there's photons hitting it, everything, so it's noisy. And what we did is we deliberately ran at room temperature, but now there are people beginning to use colder mirrors. The Japanese, for example, the one they're going to build in the Kamioka mine, are going to use liquid helium-cooled sapphire mirrors. And they think, well, they will get, I hope it works for them, they will get an advantage out of that. Eventually, LIGO will have to go in that direction. Our biggest problem right now in LIGO is a thermal noise, but it's not, it's a more complicated thermal noise. It happens to be sound waves that are running in and out of this mirror coatings. Imagine such a thing. The mirror coatings are noisy. Yeah. Go ahead, you've got a pick.
Gentleman in the front.
If you had an unlimited budget, this is the big question. If you had an unlimited budget and you could build as many detectors on the planet as you wanted, how many would you build?
Okay, I think 4 is about it. I think, I'll tell you why. You just people have been modeling exactly that question. And there is a very hard limit on the ground, which I'll just tell you what it is, which looks like if you want to do gravitational wave detection at longer wavelengths, or at periods longer than about 100 milliseconds, you have to get off the Earth, and there's a reason for that. Although we have these very elegant ways of getting rid of the acceleration of the ground, like these active systems, which work beautifully, and I strongly recommend them to you. Okay? On the other hand, they don't work against a problem which I haven't even told you about, and that is, even though the ground is shaking and you can control yourself against the fixed stars, that's what active means. The ground is also compressing, and the sound waves in the ground are going like this. Okay? And so here's our mirror. And here's a place that has a little extra density. Well, Mr. Newton's going to kill us. Here's the thing that's got a little more density. That means a little more and more mass there than there was there before. It pulls on the mirror and sucks it over to you. And that you can't shield. You can't do a damn thing about it. And so consequently, those are called gravity gradients. And they really begin to cut into how well you can do things by about 1 hertz, at 1 second. And it's hopeless, I think. Many people think, we'll try our best, but if you want to do, and there's much more science, much more gravitational wave science at longer wavelengths than it is at shorter wavelengths. So consequently, we strongly advocate this LISA mission. And for the future is going to be in space for this thing, okay? So I wouldn't want to spend, $1 billion again on trying to go below 1 hertz, that on the ground. There is an idea that, and I'll tell you, this is sort of what's ahead of everybody. There is an ambition on the ground to make a thing that's bigger than LIGO. It has to be an international project because it's too expensive. That will take us so that we can measure all the black holes in the universe, the ones that are doing the binary collapse. And in order to do that, you have to either build a 40-kilometer long LIGO, not 4 kilometers long. That's one idea. And that's $1 billion right there. That would be, if it looks like the science is good enough, we may want to go that direction. Or in Europe, they want to build a thing because they don't have any room. They want to build a big triangle and bury it under the ground. There's another $1 billion. So you're looking 10 years ahead, maybe 15 years ahead. There will be, depending on how the science goes, there may be an effort to try to build a bigger gravitational wave detector on the ground. But the big thing to look forward to is make sure that the space thing doesn't get killed.
The young gentleman up top there.
How many black holes do you think have actually collided with each other?
That's a good question. Thank you. I can't tell you that except we know a little. We see now, if you take that run we made and add to it what I know already of this run, which is sort of giving a story out of school a little bit. We sort of get an event per month. We did not improve the sensitivity of the detector. If we can improve the sensitivity of the detector, which is really the right way to go, we could get many more events per month. In fact, as you increase, and you ought to know this, and that's something that most of the people who are working on the detector are working very, very hard when we're not running. Right now we're running. We don't want to touch the detector. But once between runs, we want to make the detector better and better. And you gain enormously by making the detectors more sensitive. If you make it twice as sensitive, just twice as sensitive, get the noise down by 2, you look twice as far in the universe. It doesn't go down as a square, because we're looking at the amplitude of the waves. So you make the detector twice as good, you look twice as far out. That means the volume of the universe you're looking at is not twice that more, it's 2 cubed more, 8 times more. So you have an event per month, we might have an event every couple of weeks. Every week, maybe 2 events a week. If we get even a factor of 2. And we know how to get a factor of 2, we think we can even get a factor of 3. So if we get all the things we think we know how to do, we might be swimming in these events. Okay? So now, to answer your question, you can take that number if you know that you have an event per month per million years. Excuse me, event per month out to 1 billion years of lifetime. You can do the calculation yourself at home. No, I'm serious. How many black holes there are in a volume of 1 billion light years. That's it. That are doing this. It's 1 every billion years in that volume. One event per month in a volume of 1 billion light years radius. That's the calculation I have to do.
All right.
Yeah. Oh, I'm sorry. Hey, go ahead. You better do it.
Oh, we should feature the host of Supernova Style Science News. Please ask a question.
Hi. My question is, with the mirrors, what are they made of, and how are you making them?
Wow. You really want to know that? Okay. Have you ever ground a telescope mirror in your life?
Yes, I'm actually
I figured that's why you asked the question. Yeah. Well, I used to do that. I used to sit and then, sit there and watch, or listen to music and go, whoa. No, but these aren't made that way. These mirrors are good to, first of all, they are about that big. They weigh 70 pounds, or 35 kilograms, something like that. And they are good over the surface of the laser beam. When it hits it, is about that big. It's about the size of your hand. It's not a little tiny thing anymore. After the laser beam goes, 4 kilometers, it gets pretty big. You can't do anything to it. And so what happens is that that's just the way nature does it. It expands. So and here's what you have to get to. You have to have it to the curvature you want, to 1 angstrom. That means 10 minus 8 centimeters, so that's 10 minus 10 meters. The rippleness of the mirror has to be much better than what you have. Much, much smaller than a wavelength of light. Okay? And that reason why that's so important to us is because we don't tolerate scattering. See, if you have bumps on the mirror, even bumps of a tiny fraction of a wavelength, which you can tolerate, well, even astronomers can't tolerate that anymore if they're going to look at bright objects, because then you can spill light all over the place from ripples in the mirror. But we can't tolerate anything like that, because we don't want any scattered light. So we try to get better and better mirrors. And the thing that screws us up is not the mirror. We can make the mirror you can polish a mirror so that the bumpiness is 10 to minus 10 on the 10 to minus 10 meters on the average, the bumpiness. But you can't get the coating on the mirror to be that good. And it's probably only, the coating is probably twice as bad. It's twice as bad. And so that's our limit right now. So we keep wanting to get better coatings. That's one. So I don't know how important that is to you, but I've told you the best I can answer you. And it's made out of fused silica. Okay? And the coatings are 40 layers of dielectric coating, alternating silicon dioxide with tantalum pentoxide. I don't know if you can use that for anything, but that's what it says.
Can you talk a little bit about the calibration
Who's asking that?
Sorry, up here.
Where? Oh, up there.
Sorry, yeah.
Oh, the calibration. I'd gladly tell you about the calibration. That's actually a hard question. Okay? And the calibration is done, once you have an interferometer, you have an internal calibrator. Why? You can take the mirror. Well, let me first say, what is the calibration? You would like to know how much light change there is, change of light, there is when you move a fraction of a wavelength, and you know the fraction of the wavelength. That's really how you calibrate it. So when you move, let's say, the mirror by half a wavelength, you go at the detector from a bright fringe to a dark fringe, okay? That's one way. You don't want to calibrate it with such a huge motion. You want to calibrate it with much smaller than that. So you divide that down. And the way we do it is this way. We have pushers on the mirrors. That's how they're held. In other words, we don't let those mirrors swing back and forth freely. The mirrors are part of a servo system, which holds the fringe exactly at the same point. And this is a trick that we do over and over again. And you say, my God, if you don't let the mirrors move, how can they detect a gravitational wave? No, what you do is you don't let them move, and you look at the forces that you need to hold them so that they don't move. Okay? That's the way it's a servo system, it's called. And otherwise the mirror's dancing around all the time, and you can't damp it, and you can't do anything. So every mechanical system has a servo system around it like that. In other words, when you look at the interferometer, it looks like nothing's happening. Everything's standing rigid. But you're looking carefully at what it takes to make it stay rigid. So that's number one. So once you have that, you actually now take, and what we do is we put forces on the mirror with light. We use radiation pressure, which we measure the power, and we illuminate the back end of the mirror with light, which we turn on and off. We put modulation on, and we know exactly what the force is because of the power. And we use just something which is sort of outrageous. We're using the momentum of light to calibrate that's the only way we can get calibration signals that are commensurate with the sensitivity we have. Okay? And then we cross-check that against moving them by large motions and stuff like that. But you ask a very good question, and I'll tell you, one of the hardest things we have, it's just you all know, and then many of you may be theorists in this room, we always say we can check Einstein's equations by getting one of these black hole collisions and carefully seeing how well the Einstein equations give us all those bumps and valleys that are in the waveform. We have that in our capability. And it turns out that how well we can do depends on that calibration. Because it turns out there's a lot of different frequencies, as you saw in the signal. It runs from, let's say, 30 hertz up to maybe 500 hertz. And the calibration, you have to get the calibration of all the frequencies where you are. You have to wiggle the mirror at those different frequencies with the light pressure. And so we can't do that any better than about to 1% right now. And so if you want to test general relativity, and if we want to do better than 1%, we're going to have to do better calibration. Okay.
The gentleman back there.
So I have a question. What if gravitational waves come in opposite directions from two different collisions, and if you detect it in LIGO, so how would you see the interference?
Okay, let me repeat the question so you can hear. He's worried about it. I think you're worried about two things too. Like gravitational waves might interfere were simultaneous in their detection. That's one problem. And the other one is, I think, more real. I'll get to that. Is that how do we ever, if we have a lot of gravitational waves, which we will have, if we have enough sensitivity, how would we ever separate that out, the individual gravitational waves from multiple sources everywhere? So, first of all, there's one thing you got to know, and that's true of light, and that's also true of gravitational waves, and with a vengeance with gravitational waves, that light doesn't interfere with itself either. Okay? You can take two light beams and pass them through the same space, and they can be pushed through each other, and they don't even see each other. There's no influence at all if there's a vacuum there. Okay? Are you aware of that? That's very important. It says light, the solutions for light, when you have electric fields, you can superpose the electric fields from one source with that of another. The place where they interfere with each other is when you detect them. On a photodetector, where there's a nonlinear thing that gives you a current that's proportional to the square of the electric field. And that mixes all those different fields together. So, and that doesn't even happen for us because we can't mix the gravitational waves. So we will see gravitational waves that are simultaneously coming from different places. We'll see them superposed, and we can separate them. But just because they are their waveforms, will be there won't be discontinuities in their waves. And you will be seeing things that go through each other. but they don't interfere with each other, and they don't interfere in the detection process because we don't square the field. We can't. We look directly at the field. We look at the amplitude. So we are a linear detector. I'm sorry to use fancy words like that. The thing that does bother us will be, and that'll be a very important thing when we look into the future of the field, is suppose we get sensitive enough, which could happen in another couple of years, that we are beginning to see black holes from everywhere, and there are lots of them. I mean, when you do that calculation, which I'd asked the young lady to do, because I can't answer that, I don't know the exact number. Okay, that's the reason why you have to do the calculation. But I can do it if we sit down and do it. So the thing is that you will have many black holes collisions going on simultaneously, and you will get a background noise, an unresolved background noise of gravitational waves. And that will be the limit. Okay? And then that's about as far as you're going to be able to do. But you can learn a lot from that noise. Okay? You can learn about the density of black holes, their mass distributions, a whole bunch of stuff. We're not at that limit yet. And there will always be, and I'm pretty sure that all the way out to the edge of the visible universe, we will still be dealing with some big black holes that are bigger than the background. It's inevitable. I mean, the things here, those 30 solar mass black holes, they're pretty big. I'm sure there are 100 solar mass black holes out there too. So those will not get interfered with. They will ride on top of the distributed noise that comes from the collection of all the black holes that are radiating at us. But it's an interesting question to ask, and everybody who does astronomy has that problem. Namely, when you get to a point where you have background noise. And what happens with optical astronomy is you try to get better and better resolution with your telescopes to look in smaller and smaller regions of the sky. We probably can't do that because as I said, that even with all the detectors, they're probably not going to do better than about the size of the moon in terms of the resolution size. So we are at some point, we're far from it now, going to be what's called diffusion limited, confusion limited.
All right, and with that, it is time for us to wrap up our main program. I want to thank you all for coming, and let us thank our speaker, Ray Weiss.